Have you ever looked at a neon sign and wondered why it glows that specific fiery red? Or how we know what distant stars are made of just by looking at the color of their light? Well, it's not random at all. It's actually a secret code written by the atoms themselves. Today, we're going to crack that code, and we're going to use one of the most brilliant, most revolutionary ideas in the history of physics, Niels Bohr's model of the atom.
So, here's our game plan. We're going to start with a really colorful mystery that had scientists totally stumped. Then we'll see why the old ideas about atoms were basically on a collision course with reality. After that, we'll dive right into Bohr's wild new rules, see exactly how they solve the puzzle, and finally, we'll talk about why his amazing theory was really just the beginning of an even stranger story.
All right, let's dive in. Our story kicks off with the simplest element there is, hydrogen.
See, when you zap hydrogen gas with a bunch of energy, it doesn't just glow white like a light bulb. No, it emits light in only a few very specific, very pure colors. A sharp red, a cool teal, and a deep violet. It's almost like a barcode made of light. The big question was, why? Why only those colors and nothing in between? You know, this simple question had some of the greatest minds of the time completely scratching their heads.
To really get why that color puzzle was so tough, we first have to understand the massive problem that physicists were dealing with. Their whole model of the atom had a fatal flaw.
So, their best guess was that an atom was like a tiny little solar system. But there was a huge problem. According to the known laws of physics, that orbiting electron should be constantly giving off energy, and that would cause it to spiral into the nucleus in like a fraction of a second. This death spiral meant that in theory, every single atom in the universe should have collapsed almost instantly. I mean, the very fact that we're here, that anything exists at all, was proof that something was deeply, deeply wrong with their understanding.
So, on the one hand, you had the old idea, electrons could be anywhere, which, as we saw, leads to that catastrophic death spiral. But the universe obviously had a different set of rules. And that's when a young physicist from Denmark named Niels Bohr came along with a totally radical idea. He asked, what if electrons aren't allowed to orbit just anywhere? What if they're forced to stick to strict, specific paths?
And this brings us to Bohr's incredible solution. He basically took the old rulebook, tossed it out the window, and came up with 3 new quantum rules that completely rewrote our picture of the atom.
His solution was just beautiful, and it came in 3 parts. First, he said electrons are stuck on fixed, stable orbits. Think of them like trains on very specific tracks. Second, as long as an electron stays in one of those special orbits, it's perfectly stable. It doesn't lose any energy, so poof, the death spiral problem is gone. And third, this is the really wild part, he said electrons can jump between these orbits, but only by absorbing or spitting out a very precise chunk of energy, what he called a quantum of energy.
And the whole thing boils down to a really simple rule. To jump to a higher orbit, one that's farther away from the nucleus, an electron has to absorb the exact right amount of energy. To fall back down to a lower orbit, it has to release that exact same amount of energy. It's an all-or-nothing deal. No partial jumps allowed.
Now, this idea is called quantization, and it is the absolute heart of all quantum mechanics. It just means energy isn't smooth and continuous. It comes in these little distinct packets. The best way to think about it is like a ladder. An electron can be on the first rung, or the second rung, or the third, but it can never ever hover somewhere in between the rungs. Each rung has a very precise energy value, and this little formula here is what allowed Bohr to actually calculate the exact energy for each of those rungs in the hydrogen atom.
Okay, so we've got these weird new rules about electrons jumping up and down this energy ladder. But how in the world does that connect back to our original mystery, that barcode of colored light from hydrogen? Well, this is where it all clicks into place. Here's the brilliant connection. When an electron jumps down from a higher rung to a lower one, that chunk of energy it has to get rid of doesn't just disappear. It gets shot out as a single particle of light, a photon. And here's the kicker. The amount of energy that photon carries determines its color.
And this, right here, is the solution to the whole mystery. The size of the jump down the ladder determines the color of the light. A really big jump releases a high-energy photon, which our eyes see as violet light. A smaller jump releases a lower-energy photon, which we see as red light. And it just so happens that all the jumps that land on the second energy level, what's called the Balmer series, they release photons with the exact energies that correspond perfectly to that red, teal, and violet we see in hydrogen spectrum. It wasn't random at all, it was physics.
So the key takeaway here is that since every element has its own unique set of energy rungs, it also has its own unique set of possible jumps. And that means it has its own unique set of colors it can emit. This spectrum is literally the atom's unique fingerprint. It's how astronomers can look at a star billions of miles away and say, yep, that star has hydrogen, just by looking at its light.
Bohr's model was an absolute game changer. I mean, it perfectly explained the hydrogen mystery, but like so many great breakthroughs in science, it turned out to be an imperfect masterpiece. And we really can't overstate how huge this was. For the first time ever, a theory connected the invisible, bizarre inner workings of an atom to something that we could actually see with our own eyes. It was this incredible bridge between the weird new quantum world and the physics everyone was familiar with. It worked.
But science never sleeps. And as physicists started looking closer and trying to apply Bohr's model to other things, a few cracks started to show.
Turns out, the model's beautiful math only really worked for simple hydrogen. The moment you tried it on an atom with more than one electron, like helium, the whole thing just fell apart. It also couldn't explain why some of those colored lines, when you looked really closely, were actually made up of several even finer lines. And it had no answer at all for why those lines would split apart when you put the atom in a magnetic field. So, where does that leave us? Well, Bohr's model wasn't the final answer, but it was an absolutely vital stepping stone. It introduced this world-changing idea of quantization that is now the bedrock of all modern physics. It was a brilliant, flashing glimpse into a new reality, showing us that the world inside the atom was far stranger and way more wonderful than anyone had ever imagined. And it threw the doors wide open for the next, even weirder revolution, full-blown quantum mechanics, where electrons aren't little planets at all, but strange fuzzy waves of probability. The universe's code, it turned out, was even more complex and beautiful than Bohr could have ever dreamed.